Let's get started. Welcome. Welcome to the first session of CytoData. I am Tom Nijl from CytoSmart. Just to make it clear to everyone, CytoData and CytoSmart have nothing to do with each other. They just both like to put the name Cyto in the name. CytoData, for those who don't know, is an organization that focuses on bringing biologists together who are interested in dealing with bigger amounts of data and are in need of the data science technologies to apply to their data. CytoSmart is a company which creates live imaging microscopes for analysis and of course also does some computer vision. I will be talking today about transfer learning and how to use transfer learning together with machine learning. We will go into examples for transfer learning, focus more on beginners, on newcomers to deep learning, and we will at the end look more into the literature to look into more in-depth analysis of what we can do with transfer learning, how we can go further with it, and how we even can use it for unsupervised learning. So, first question, what is transfer learning? Transfer learning is the, and I just told this, I should remember that I made slides for myself to help me. But yeah, what is transfer learning? We will go into some classification problems with some code examples. The code can be found in the show notes, where you find a GitHub link to, to the GitHub, and we will go in the papers in a bit more detail in more interesting cases, which were too extensive to all go through in codes. So, what is transfer learning? Transfer learning is taking knowledge from one domain, from one task to another. So the most basic example, which I just stole from every article I read about it, you want to learn the guitar, you already can play the piano. That means you can take some of that knowledge and transfer it to the guitar, making it easier to pick up the guitar. You learn it faster, you need less time, less examples. If you compare it to somebody with no musical knowledge whatsoever, well, that person will learn the guitar way slower. He has no knowledge to transfer, so it will take more time, more resources. The same holds true for machine learning concepts. Let's say we want to have a model that can separate 101 different types of foods. But we already have a model which can separate over 1,000 different classes, ranging from everything. Some of them foods, but some of them plants, some of them, computers. We can transfer that knowledge because, yeah, the objects still kind of look the same. It just needs to learn a little bit more. If we have a totally oblivious model, it will take way longer for that model to train, to get there, and to reach the same levels that the other model could do. This is literally the example we will do in codes once we're getting to the codes. But first, a little bit more about transfer learning, because transfer learning basically has two tastes: changing the domain or changing the task. The truth is, most of the time you do both or a little bit of both, but yeah, we will look at them. Changing the domain means that we change the data. So let's say we start with pictures of ImageNet. These are just a lot of random pictures, and we try to classify them. So, well, I think every human would agree this is a motorcycle. we changed the domain, so we now fetted different images, but we keep the task the same. We still try to classify it, but now I want to know that this is a cat. This is one of the most common examples that people do. But the other one, changing the task, means we keep the same images, but we expect something else from our model to do with it. So instead of classifying that this is a model, we want to segment every pixel. This is motorcycle, this is the human on the motorcycle, and we get a segmentation. So now we change the tasks. This is the example we will look in at the end, how Facebook did, well, exactly this. Yeah, exactly this in their Mask RCNN paper. The use cases are pretty simple. Faster training, training with less data, and like I promised, also you can use it for unsupervised learning, specifically self-supervised learning. But first, some codes. For those who want to follow along, I wrote a code in Python 3.7 with TensorFlow 2.3. I have noticed that TensorFlow 2.2 and 2.4 both give you some errors of functions that are renamed or not there. Sorry, I will try to point it out so you can easily change it if you do not want to install a different version of TensorFlow, which I fully understand. This is the code that is directly from GitHub. In here, I will first show you a trained model. Within TensorFlow, you can download a few pre-trained models. Those pre-trained models are all trained on ImageNet datasets. Like I said, this is datasets where they classify thousands of pictures in all domains. All those images are RGB camera images, normal cameras, no really specific zoom in. I did check, there are no images of cells or through microscopes in there from what I found. Maybe I'm wrong, but there are a lot of images. But if we are having a look at it, oh, by the way, all the notebooks are pre-run. That is because it takes a few hours to run them, and otherwise this session would take way too long and would become way too boring. So yeah, this first cell, not that important. That is just because otherwise it gives errors on my computer. Here we load in the efficient nets, one of the many models which is in TensorFlow. If you want to run this yourself on a lower version than 2.3, you will have to replace efficient net for something else because that was introduced in 2.3. Next up, we open the image. I was hoping that it would show me the image, but apparently it's decided to not do that because why would it do what I wanted to do? So I have here a picture of my cats. And if I now run the model on it, I just try to make a prediction. I will see that it is 15% Siamese cats, also 15% Egyptian cats, and after that a quilt, apparently. I think he confuses the chair for it. But this is the normal behavior of a classification algorithm. If we continue, I here took apart the whole model so that I can see the activation of each individual layer within the whole model and can visualize them. So let's have a look. Here we can see in the first, these are all the filters of the first layer, and we can see that it reacts on the basic shapes like we expect. The first layer of a neural network, we do expect to see some edge detection, some areas that react on more even colors, etc. And if we're looking a bit further down, we will find here the more complex layers where it, as a human, becomes harder and harder to understand what the model is actually seeing. These are thousands and thousands of filters and even millions of parameters if we need to sort through this by hand and pick out which ones are interesting, which ones are not interesting, and try to figure out which one we want to transfer to another one, well, we would take even more time than just training the model from the start. So that is not what we're going to do. In here, in the first example, ImageNet to foot 101, we go through the first steps again, just loading it, getting a data generator, and we visualize here part of the data set we're working with. So we see some hummus, some omelets, oyster. Always good to visualize your data, then you know what you're dealing with. Next step, we just try to load the model, and we're going to continue training this model, but on a new data set in order to transfer the knowledge. In here, we take the pre-trained neural network, and we are going to try to train it without the pre-trained weights and with the pre-trained weights to see the difference. So here we have the pre-trained model, and we're not including the top because the top is meant to go for those thousands of classifiers, and we want to bring it back to the 101 classifiers which we have, the number of classes. So we just add another new max pooling, a dense layer or fully connected layer, and compile the model with Adam optimizer and category. Does not really matter, but we now have a model. We train it, and we here train it without any pre-trained weights, in other words, with random weights. Well, you can see here that it takes between 250 and 400 or almost 500 seconds to train each epoch. That is the reason why I give you pre-trained notebooks, because nobody has time for that. And here we see the accuracy slowly going up. The training goes up from 0 to, I look over here, almost 0.4 at the max after 20 epochs. And the loss goes down, thank God. But now we take the pre-trained network. So this network already has some knowledge about basic shapes, has already seen a lot of images and has some general understanding of it. Well, we do the same. Nobody will be surprised, but the training time is about the same. But the accuracy after one epoch is already higher than after 20 epochs of no training. So that is already a huge improvement in only the time. And for the loss, we see the same. But something else I want to point out, we also see that the loss function for the test data set goes up already quite quickly. The lowest point seems to be, well, here about at 2 epochs, and afterwards goes up while the training loss goes down, meaning that after 2 epochs it is also already starting to overfit. But we're CytoData, so most likely not a lot of us are in the need of labeling images of food. So how does it deal with this data set? Let me see this. I hoped I had a clearer link here, but in the link here you can find it. This is a malaria data set, and it has basically two classes, uninfected or parasite or infected. And this is once again a classification problem, but the images are way farther away from the images we're used to in the ImageNet. So let's see how it deals with these. The setup is the same. The only difference is now I have two classes I try to predict instead of 101. And we first start to train with random weights. We can see that a lot of the timing is a bit lower because the data set is a bit smaller. And we see that it trains and it slowly goes up till, well, the maximum here for the training set is, I would say, 95 and 98 for the training. Now going down, same story, but this time with the ImageNet data, we see again it starts way higher. Even after the first epoch, it apparently still could take some of those basic features it learned from the ImageNet and transfer it here to a completely new data set, which is in a domain way farther removed from the original ImageNet. And I don't know where that spike is coming from. I tried to look into it. Sorry. We see also here that after 3 epochs, 4 epochs, the overfitting starts, just like with the foot 101. If we look here at the accuracy, even at the end, well, we see that we gained an extra % in accuracy in the validation sets, as well as in the training sets, which is great. I mean, higher accuracy with the same amount of time, why not? I am constantly checking the chat. If you have any questions, just shoot them in there and I will try to answer them if I know the answer. If not, I'll make something up. No, I will try to be honest. But something I touched on already a few times is, of course, the training time. We do not always have that much training time. Oh, let's see. Do you know why the transfer model tends to overfit? Yeah, basically because the model is already further in what he is learning, he is already further ahead, he starts to overfit. The only way that this model can perform better on the training data set is to look too closely to the training data set and forgetting to generalize. If I would take the model which is trained on random data and would let it continue training, I would see the same pattern at a certain point. It only would happen way later. It is just the head start which it had thanks to the transfer learning. So the training time is, of course, sometimes a problem, or sometimes we have the problem that we do not have that much data in our new training sets. But if we look again to the visualized data, the first layers are very basic. Maybe we don't need to add them to our model for retraining. Maybe we can just leave them for what it is and see them as a pre-processing step. That, my friends, is frozen layers. Frozen layers, well, means that some layers we will freeze during the training. We will make sure they are not updated during training steps. With that, we reduce the amount of parameters of our model, meaning that we need less data because less parameters means less data in order to optimize them. We need less time, but it also means we have less degrees of freedom, so most likely our performance will go down. At least our performance will go down if we have enough data. For this example, I choose to use the Food 101 dataset again, given that it is more challenging, although the malaria would have been more suitable. Yeah, it was just too easy. So we go through it. Most of it is the same. Only difference we see in here is that the moment I load the model, I will set certain blocks to false. So I will freeze it in blocks. If you're looking into the paper of EfficientNet, you will they will explain what all those blocks are. I just took them for granted. But blocks and layers for the purpose of this talk are kind of interchangeable. One block is just multiple layers together. So first off, we freeze the first, I said layers, but this is actually blocks. Well, I freeze the first 4 blocks. With that, I have 100,000 parameters which cannot be trained, but still 4 million which can be trained, because like most neural networks, most of the parameters are in the top layers, not in the bottom layers. Too bad for us at this point, but let's deal with it. So yeah, we train it, and if we go here to the bottom, we see that we have a drop compared to the model which had no frozen layers. Let's have a look here. So after 20 epochs, we see it took, well, roughly 250 seconds. That varies quite a lot, but between 250 and 500 seconds an epoch, and we got an accuracy at the end of 93.8% for the training and 64.5% for validation. So we see a slight drop, but it is not by a lot here, given that we did not freeze too much of the whole model. But our time, well, almost halved our training time, which is great, especially if if time and training of the time is any concern for you. Of course, the amount of parameters is not that much lower, so that means that we still need roughly the same amount of data in order to train this. You could say that you need 2.5% less data, but in most data sets that is not really a significant difference. If we go a bit more extreme and we freeze 8 blocks, we can see that it is already a bigger part of the model that is being frozen. 500,000 parameters cannot be trained. And we see an even further drop in the time. But we also see quite a drastic drop in the accuracy. I know I focus on the accuracy, but accuracy is easier visualized than the loss. If you train a model, looking at the loss, of course, tells you a little bit more normally. But yeah, this is not, this is actually in between both worlds. We have not frozen a lot, and we have not reduced the amount of parameters by a lot, and we have not reduced the time by a lot compared to only freezing 4 blocks. So, what about freezing the complete model? In here I froze all the layers except the new top layer. So those are is the fully connected layer or the dense layer after the max pool, which I added to it. And now I train this, and now we see a real big reduction in the amount of trainable data. So this is a good solution if you have a limited amount of data to train on. But of course, that comes with a very significant drop in accuracy, both for validation as for training. And the reason we see such a huge drop in the accuracy is because I do have the data. I do have the data to just go on, to just train with it. I don't need to freeze so much. But if I had smaller models, I could even see an increase in accuracy because I postpone the moment that the model is overfitting. Oh, I'm not used to talking so long to myself. But yeah, this is these kinds of methods is also what you can see in Microsoft Azure Cognitive Services. They provide a service where you can send some data and they will give you a model back which is trained on your data. They need quite small amounts of data in order to classify it or to give you a working model, and they do it by freezing a lot of the model. Only the top layer or the top two layers are unfrozen and actually be trained, and the model they pick is very generalized, or at least very generalized to the data they think the customers will send to them. Any questions? Type them into the chat. I am reading it constantly. If not, this is how far we will go with the code. Have a look yourself into it. But that's not how far I want to go with the theory. Because, like I said, you can do even more with it. This here is a basic example of mask RCNN. Mask RCNN is a model which is trained to give you a segmentation of objects. So we can see there are here some kids playing football, and here at the end each individual kid is segmented into a pixel segmentation as a separate object. What Facebook did, they picked the backbone of their model over here and replaced it with a pre-trained ResNet 50. And that pre-trained ResNet 50 was trained on ImageNet, the COCO database, and I believe also CityShape database, meaning they had a very generalized model that already had seen a lot of images in the world. And they put it in there. They froze that part at first, so they would only train the top. And how this top exactly works, I recommend you to read the paper. I will not go into it, but they only trained the top that would actually segment it. And once the top of the layer was a bit up to speed with the backbone, they unfroze the whole network and they trained the whole network. So both the pre-trained and their new heads together in order to get the boost. With that, they got the boost that the head, which was untrained, actually got up with the already very much trained backbone of the network and speeded up their training by a lot. The other one, which I just want to point out, is self-supervised learning. Self-supervised learning is something that goes really well together with transfer learning. To put it simply, you try to come up with some kind of tasks for your model where you can automatically generate labels. You train first on those automatically generated labels, and afterwards you try to transfer that model to your smaller data sets. because you automatically generate the labels, you don't need to have any labels for it whatsoever. And that is the basics of self-supervised learning. Let me go through a few examples. Unfortunately, self-supervised learning works kind of hard on cell data, and you will see in a moment why. This is the first one that I want to point out. This is self-supervised learning based on rotation. I have here a picture of a cat, and I just take a random database and I don't care about the label, so I don't know that this is a cat. The model does not know that this is a cat, but I randomly rotate it in one of 4 positions, and I think you can can see what the 4th position is. So a 0, 90, 180, or 270 degrees. I give it to the model, and I want the model to predict in which orientation the image is located. By doing so, the model needs to learn that every cat has the eyes below the ears, and the nose is below the eyes, and which is below the ears. That logic is needed in order to understand if a picture is rotated or not. And by doing so, you can train the model on a large data set. It will learn a lot of basic features about cats, and you can give it then a smaller data set of cats and dogs and just train it on that part. This would, of course, not work on cell biology data, because there is no orientation, there is no up and down, making this kind of pointless. Another example of it is EXEMPLAR. What you do in the case of EXEMPLAR, oh, by the way, I picked a slight modification of EXEMPLAR, which is explained in the paper Revisit Self-Supervised Learning. Well, you can read it here on the bottom. Yeah, I will make the PowerPoint available so you can look through it. But they used the same technology as FaceNet. But what they did, they picked the original image, they made an augmented image, and they picked a different image. They threw all 3 images through the model, and they said, okay, model, you need to learn that the original image and the augmented image are the same and very close to each other, where the different image should be farther away from it. This way, you can train your model to be immune for data augmentation on a data set that you don't have to label. The paper also goes into, the paper does focus on natural RGB camera images, like most papers do. But theoretically, this is possible on cell data. The downside is this was the worst example they gave of the self-supervised learning. This one performed, the worst of the ones they revisit, which is kind of bad, but kind of understandable, because the only thing you do is train to be immune to data augmentation. And most of the time we already do that by applying data augmentation to the data set itself. But still interesting. There is then other methods, and that is scraping metadata. Metadata can be anything you can find that is related to the image, of where it was taken, the batch it was in, everything that is automatically generated with it, which you can use to train on it. In this case, well, Instagram, where people tag everything with, I don't know what, I actually also do not want to know what is all tagged with it. This I saw beautifully used in a cackle competition some time ago, where the question was, can you train a model that can answer questions? And well, the people were content with the data set they got, but they want to have a bigger data set. So they scraped all of Stack Overflow on questions and tried to predict the upvotes of those questions to pre-train their model on. Once they had done that, they picked the smaller data sets and only worked on those. This is, of course, only possible in some kind of an automated sense. So if you want to apply this in cell biology, you need to have some mass throughput system in order to have some kind of metadata to work with. And lastly, I just want to mention this because it is also a good example. The first speech recognition software all used to be trained on predicting the next words. Hey, I had a nice animation for it, and that got away. Damn it. Anyway, by taking away part of the sentence and trying to ask the model to predict the next one in there, that is unsupervised. You don't need to label them. You just need to scrape a lot of text. You go through it. He tries to predict it, and he starts to learn how sentences are built up. It starts to learn that after the word guide, if he sees the word guide to the, it's very likely that the next word is galaxy, more likely than the word grilled cheese. That's the word. Anyway, also in those cases, you use the sequence. Other places you can see it is, for instance, in genomic data, where you also have a sequence. With the microscopes we use at CytoSmart, where you take we take an image every hour, so we also get a sequence, and we can use that sequence to predict data. It is also already used on to work with sequences in images in papers. I've seen from the Hong Kong University, where they used it in order to predict weather. Okay, so not per se pictures, but convolutional neural networks, that's the important part. And they try to use the predictions of it, and they also use unlabeled data because they just take the first 5 images of the weather and try to predict the 6th one. And with that, I believe I'm at the end of the things I have to say. Are there any questions? Maybe as crazy as you want, even if you just want to know if certain things look interesting, just shout. Oh, sorry, I will read them out loud, otherwise we'll be boring. Hi Tom, thanks a lot for the great first tutorial. In your experience, how different can be the original task from the repurposed model compared to the new task? Will still be useful. For instance, would the first layer of well-trained regression model be useful for classifying based on similar inputs? In my experience, from what I noticed, and also what I especially noticed here with the malaria data sets, here we see that the domain is very different and it deals with it very well. But also when you want to change the task, normally as long as it needs to have a similar understanding of it, it is fine. Let's take these pictures, and I have now a pre-trained model on a malaria data set, and next up I want to segment the infection itself, which I think are the purple dots in here. I'm not a biologist. It already had to learn that the purple dots were of any significance, so it already had some knowledge of it, which it can apply here to segmentation tasks. in which case the task is very different from segmentation to classification. The moment you go too far away, so what you saw over here, where you try to use augmentation and try to train it to ignore augmentation, you see that it does not really need to understand what a cat is. Because all it needs to understand is if he can reduce the augmentation. And so then the tasks, the needed knowledge is very different. Yella, what is your next topic? Oh, sorry, did I answer your question? Maybe I should ask that. I will go to the next question. Yeah, what is the next topic? Don't know yet. I have some ideas, but we will discuss that with CytoBoard. Oh, I should not forget, you can follow, if you subscribe to us on YouTube, on LinkedIn or Twitter, we will keep you up to date for next tutorial and next sessions we will hold. Any more questions? I think this is the part of the session I will cut off before re-uploading it. Okay. Thank you, and I hope to see you next time with a different subject. Same subject would be really boring. Goodbye.